Thank you. Thank you. How are you feeling? But it's the end of the day. Wow, good job staying attentive, staying in all the talks. Incredible. Now I realize one thing. I am the last person standing between you and dinner. But also, conversely, you are standing between me and dinner. So let's get through this fast, and then we can go enjoy. But hopefully, together, we learn some really great things. My name is Tejas. That's pronounced like the word contagious, if it helps you pronounce it. It is an exotic Indian name, and so I apologize for my name. And I live in Berlin, in Germany. So I came here from Germany, and I'm really excited to talk to you about some interesting things. But before we do that, since we're at the end of the day, this conference has been so amazing. So for the organizers, the speakers, can we just give it to them? Oh my goodness. What did we see? We saw how you work with 3D stuff. We saw how you test. We saw how you work with observable. We saw so many things. You know, I learned a lot here. And I'm really thankful for this conference and this community. And lastly, at the end of the day, we're here to talk about what? WebAssembly. More shortly, more concisely known as WASM. We're going to talk about kind of why it's interesting. We're going to talk about why you should be interested. And we'll do some fun coding exercises together. But first, let's just quickly talk about some facts and figures. Numbers. Everybody likes numbers. So let's look at some data. When I last checked, around 87% of all browsers already ship with some type of functioning WebAssembly. And this is really interesting because this is the fastest browsers have moved to support things almost in unison. And that's very, very exciting. So if you can use it, if you think you can use it, you probably can. Secondly, Figma, popular UX design tool, was able to increase their performance 3 times, porting parts of their app to WebAssembly. Now it is just fast and performant, and everybody knows when things are fast, what happens? Users are happy, yes, and if you're a for-profit company, you get rich. Secondly, a DNA, like gene sequencing tool, fastq.bio, was able to get 20 times the performance they used to have with WebAssembly. It just makes things really fast. And in this talk, we're going to talk about how it makes things fast and how it could possibly, hypothetically, theoretically, practically make your things faster. But I think the most impressive statistic of all is this. Really old code base, AutoCAD. How many of you know of AutoCAD? A lot. It's popular, and it's old. It's a C++ project. And fun fact, AutoCAD is older than me. And what they were able to do was take this old C++ code base, make it run where? In the browser. And what that means is if it runs in the browser, it can run on the web platform, and the web platform is universal. It can kind of run everywhere. This is huge. This has not been, it wasn't so easy before. And so what we're here to talk about is all of the fun things we can do with WebAssembly. Like there are a number of tech companies, big ones, small ones, startups, whatever, all over the world doing powerful things with WASM. eBay built like a pricing mechanism with WASM that makes those transactions faster. PS PDF Kit is a PDF workbench kind of tool that will bring like Acrobat-style desktop class functionality to the browser using WebAssembly. Google built an image compression tool. Now, if you know about image compression, you know that like as the resolution goes up, it gets very expensive. It requires more performance power. And they built this tool called Swoosh using WebAssembly that is fast. Microsoft, how many of you have heard of Blazor? Blazor is, okay, like 6. Blazor is a way to kind of run Objective-C in the browser. I won't get too specific there. And lastly, 2 game engines, Unity and Unreal, are able to execute on the browser with WebAssembly. This is very exciting stuff. What that means is we're able to see things in the browser that previously used to be desktop class. Very, very exciting. But some of you may be asking, okay, but why? Right? I have a desktop, it works. I have a Mac, I have a PC, I have Linux, things work. What's the point? The point is the web needs help with performance. We're using JavaScript, and it's great. You can do a lot of things, especially asynchronous things with observables, with promises and so on, but we're limited. There's a ceiling. Secondly, WebAssembly moves the priority, the focus context, from the OS to the browser. This means you can do more exciting things on the browser, and guess what? Browsers run everywhere, even on your phone, even in like your car dashboard. That's incredible. And lastly, it makes the web platform more inclusive. You see, right now, everything is JavaScript on the web. Right? You say, oh, but I write TypeScript. Yeah, that compiles to JavaScript. Oh, but I write reason.ml. That compiles. Everything, at the end of the day, is JavaScript. And that's what is run on the browser. Now, WebAssembly allows theoretically, any language that has some type of static typing to compile to WebAssembly and execute in the browser. This is already true of like C, C++, Rust, and even there's a variant of TypeScript called TurboScript that compiles to WebAssembly that you can use in the browser and get some performance benefits, arguably. But now that we know kind of how companies were able to get benefits and why it's such a powerful and inviting technology, what actually is it? What actually is it? And for this, I'm just going to exit out of this keynote presentation here and go to the browser. I'm going to find WebAssembly. I'm just going to go straight to the source, compile from source. And what we see is that big enough? It's big enough here. Is that big enough on the screens? Great. And what we see is it's a binary instruction format for a stack-based virtual machine. And it's really exactly what it sounds like. It is a format for binary instructions that executes directly on the CPU. So it's fast. You don't have a lot of the dynamic checks that we have in JavaScript. It's designed as a portable target of compilation of, look at this. This is a little bit funny, high-level languages like C, C++, and Rust. And you laugh, right? Because see, these are, what? This is high-level? How is this high? JavaScript is high-level. But how? Because everything's relative. And so from JavaScript, these are low-level, and we're mostly JavaScript developers here. But if you think about assembly, right? You think about binary, ones and zeros. Where is C, C++, and Rust there? It is higher level. So these languages are higher level, and they compile down to binary formats, ultimately enabling deployment on the web for client and server applications. What that means is you're able to write things in C, C++, Rust, whatever, compile to WASM, and then run in the web. Very exciting. That's kind of how AutoCAD works on the web and everywhere. And so we've kind of defined what it is from the source. But how does it work? And to understand how WebAssembly works kind of in the browser, we need to revisit how JavaScript works in the browser. And I'm sure all of us know this, but let it just be a refresher. JavaScript, when your browser downloads JavaScript, what happens? What happens to the string? It gets tokenized. So the string is just a plain text string. It becomes meaningful. So words like const, words like let, words like for, words like function with a star next to it, they become things that mean something. They get tokenized. And there's a very gentle difference between tokenizing and lexing that we will not get into this. We'll just call it tokenizing. But once it's tokenized, once the string becomes meaningful, it gets parsed, right? It becomes, from a string, it becomes something called an abstract syntax tree. It becomes a tree that represents each piece of meaningful information. And from there, and this is, by the way, this is where Babel is able to do really cool things to your code. This is how your JSX, like less than signs, will become React.createElement with a process called transpilation. And then after that, we have code generation. So once it's parsed, once it's meaningful, we can then compile that to something way lower level, like the ones and zeros. But this takes a lot of time in some cases. And lastly, that code is executed. Right? Now, as you can see, there's a lot to be done here. With WebAssembly, really similar things happen, but the WebAssembly module you have in most cases is usually generated code. And that is executed. But the question is, how does it execute? And those details I shared, by the way, are different according to different engines and execution environments, and as are the steps we're going to show here. How does it execute? Depending on the environment, JavaScript goes through an interpret step. And what does that mean? Well, JavaScript is dynamically typed, so you don't really know what's what. You do const a equals 42. Is a number? Is a string? Is a function? Is a null? Is a we don't know. So the interpreter does what? It interprets that and kind of draws meaningful conclusions. From there, it's passed to, let's call it an observer. Usually, and this is extremely broad strokes. The goal is to get a very nice overview of how these things work, and then I'd welcome you to dive deeper. The observer in most JavaScript engines will kind of just watch the code for things that are used often, things that are used a lot, and will, over time, realize, hang on a second, this function is called like 200 times. For example, we looked at some of the observables, right? This this tick function is called so many times, it will pass it to an optimizer, and the optimizer will then make the function hot. It will make it fast. And lastly, you might shoot yourself in the foot. If you're not careful with your code, you could do something called a deopt, and this kind of breaks the recognition of the observer and takes you back to the observed step. So then, so you kind of lose some performance if you're not careful. Now, how does WebAssembly execute in contrast to this? It's quite different. We don't need an interpreter in WebAssembly because we write statically typed languages. We write Rust and C, and so these, everything's known ahead of time. We don't need that. We don't really need an observer because things exist. We do have an optimizer, but that kicks in at a very interesting stage. So to my best estimation, now I need to preface this, I'm not a browser engineer. I'm not a JavaScript engine engineer. I'm just a really curious person who will sometimes get stuff wrong. But this is what WebAssembly looks like when it executes. There's usually, in most environments, there's a two-tier compiler. And what that means is priority number one is making things work. And so tier one will load your code and compile it and just ship it to the user, make it work. Tier two will closely inspect the code for things that can be optimized, things that can go faster, and will hot replace them into tier one. Right? And so what you're able to do in the WebAssembly setup is you skip a few steps because everything's known ahead of time, but you can keep optimizing. Because of that, we have some really, really big performance benefits, but also these compilers are really cool because they are streaming compilers. So it's not uncommon. If you have a huge app, you ship tons of code to the user, like 12, 15, 5, maybe not 500, but 50 megabytes or something. And if you've ever watched a talk by any Chrome developer advocate in your life, ship less code is what they'll tell you. So how do we do that? Well, the streaming compiler is really cool. As a chunk of your code comes in from the network, whenever it becomes executable, it's ready, it's compiled, it's ready to go. So the network is no longer the blocker in this case. And that makes for some huge performance benefits. We talked a lot about theory. We talked a lot about how things work, like if you're able to visualize things. But let's put it into reality a bit and look at some real-world examples of cool things people have built with WebAssembly. And to do that, let's go to the browser. Should I make this full screen? Yeah, let's make it full screen. And the first example I want to show you is, I didn't build any of these, by the way. I just think they're really cool and kind of show off the potential. The first example isn't even WebAssembly. It's a precursor to WebAssembly, something called asm.js that would evolve into WebAssembly. And what it is it's a game of chess between two machine players. One of them is optimized with asm.js. The other one isn't. Now, they both have 200 milliseconds to figure out what's the best move to make. The asm.js one can do calculations faster, so it will probably win. And this is what it looks like. I'm just going to start a match here, and we just watch them play. And what you see over here on the right is this graph of the likelihood that the blue will win. And over time, since it's able to do calculations faster, it's pretty much the undefeated champion. And there we go, the asm.js optimized one wins. What that means is the compute power is faster. Second example is, so I grew up with sometimes Windows, sometimes Mac. And when I had Windows, I was like, this is amazing. I can play all the games, but I can't use creative software. I like Final Cut Pro or Logic Pro or some of these specific Apple apps. And I was like, I don't get the nice feel of the Mac. When I was on a Mac, I was like, this is beautiful, but I can't play games. Like Apple Arcade is nice, but come on. I can't play real games. Controversial. And so there was always this operating system lock-in. With WebAssembly, since everything's in the browser, it doesn't exist anymore. And so here's a demo of the Unity engine in WebAssembly. I have my sound on. And as you can see, I'm playing this character here. And this is 3D graphics. This is a real, it's not one of these baby games. It's a real game. And I'm trying to win, but, stop, shoot. And so I get really invested, so I should probably stop. But this, look at it, 60 frames per second, buttery smooth in the browser. Isn't that amazing? Isn't that amazing? And then whoa, hey! Okay, did not see him. Number 3 is the creative apps. You can do that too. This is a video processing system in the web using WebAssembly, and I love this one. I want to show you this. So there's a nice video here, but you could even use your webcam. And so I'm going to switch to my webcam. And what you'll see, hey, it's me. I'm there, I'm here, I'm everywhere. And it's nice and fast, you know, like it's not, look, I'm waving, it's smooth. But when I do something like processor intensive, watch this. Let's go Gaussian blur. And look at that, like that's nasty. You see that? It's not smooth. Look, I wave. But if I disable JavaScript here and let WebAssembly do its thing, watch. Look at that, way faster, right? Slow, fast. And that's the benefits of WebAssembly. And so I think I don't need to convince you anymore. It's fast. I thought us on the web, we like to build things for fun, for curiosity. So I thought, what's the most interesting thing I could find with WebAssembly that really like is next level? Maybe not entirely necessary, but let's just see. And you're not going to believe this, okay? Someone, actually a very well-known author, has like ported Windows 2000 to WebAssembly. And here, look, it's like totally a thing. Look, watch. This is Windows 2000 running in my browser. I think that's absolutely incredible. I could even go here and like, look, the memory is limited, but I could go here and I have all the like Windows 2000 things we love. Look at this, I could totally play this right now, look. There you go. Thank you for helping me, wow. So I'm just going to keep playing this for the rest of the talk. I hope that's okay. You know, my plan is actually to win this and then show you that cool animation that happens, you know? Who remembers that? All of you. I actually found it. Winning. I found it on the web here. Somebody did this with WebTech, like CSS and stuff. Isn't that amazing? Anyway, we're getting sidetracked. But all that to say, you could do some really, really cool stuff with WebAssembly, and this all works. Now, I need to give credit to this Windows 2000 one because it blew my mind. And this is this genius right here. Zoom in, Fabrice. It's French, so I'm probably going to say it wrong. I apologize. Fabrice Bellard. Really, like if you want to follow someone on the internet or Twitter, this is the person. Genius. So we looked at some examples. We looked at how it works. And so after this, your interest is probably piqued. And you're probably thinking, well, hang on, I think my computer is frozen. It's not very good. No, right, it was Keynote. Let's go back here and play. Right, so I probably piqued your interest of, you know, this is cool. Your next question is probably, how can I play? The Windows virtual machine is killing my browser, I think, or something's not working. So maybe it's this thing. Let's close this, close that, close that. Let's go back to Keynote here, and let's see if I can get my next slide. Yes, all right, so you're going, how can I play? And there's really many ways to play if you come from a C or C++ background, or if you come from other backgrounds. And if you come from C or C++, there's this tool, Emscripten. It is a drop-in compiler for C and C++ to WebAssembly. And so theoretically, you don't really have to change very much or anything. You kind of, instead of compiling the typical way with C or C++, you write emcc, compile to Emscripten WebAssembly. But I did learn C++ at some point and forgot it like immediately. I'm not gifted here, but there is something that I am interested in, that's Rust. Rust is a language that I believe is like modern C. And it was created with amazing interoperability with WebAssembly from the get-go. Moreover, here's some reasons I think Rust is absolutely incredible. There's libraries for Rust that enable really powerful usage with WebAssembly. One particular is called WASM-BindGen. And it's exactly what it sounds like. It's WebAssembly, bindings in Rust, and then code generation from Rust. There's WASM-Pack, which takes your output from WASM-BindGen and bundles it up with Webpack. You can literally npm publish a node module from here, and it will just work. But there's also library work being done in the Rust ecosystem. There's especially something called WebSys, which is the web APIs. How many of you know about web APIs? You work with web APIs all the time, right, of course. They implemented them in Rust. So you can just use them in Rust. And these are generated from something called WebIDL, which is the Web Interface Definition Language. Browsers are generated from this stuff. So it's going to be up to date. And lastly, JSConfAM19, which is the JavaScript APIs. again, implemented with WebAssembly. Now, what does that mean? In JavaScript, you have a global WebAssembly object. And from Rust with JSS, you can call WebAssembly in WebAssembly. You could go down all kinds of weird trails here, but let's not. We're short on time, so I'm just going to say, you know what? Presentation's all over. So let's just code. Let's code some stuff. And I want to show you how you can get started right now, practically. Okay? This shouldn't take too long, but if you're on Wi-Fi, do me a favor, go off, because I'm going to npm install up in here. Let's hope this works. npm init, and we'll type Rust Webpack and the name of our project, so JSConfAM. Let's just call it that. And this, I've timed this multiple times. This takes, I believe, maximum 1 minute. So it's, you know, I could just stand up here and tell you jokes, but hopefully it's faster. I could think about jokes. Why don't you tell me a joke? Why all the pressure on me? You tell me a joke. Sorry?
3JS and WebAssembly walk into a bar.
And then what happens? That's the joke. All right, it's done. Good. See? Wow. We don't even need a joke. Okay, so dependencies are installed. Let's go in here, JSConfAM. And what we're going to do is look at the code, okay? And it's very similar, actually, to JavaScript. Because in JavaScript, you have a package.json, which lists metadata about your thing. You all know this. In Rust, you have something called a cargo.toml, okay? And what cargo.toml is kind of exactly like package.json, but in Rust. It lists your dependencies and some other stuff, but that's basically it. We're going to call yarn start here. Yes, it does work with yarn. And it's going to build for us. Now, this build step will take some time because it pulls dependencies down. But while it's building, let's look at the code. We have a lib.rs file with a whole bunch of stuff we don't need to concern ourselves with for this talk. Let's just get rid of that. And what we see is what? Does this look familiar to you? It's using WebSys. It looks like JavaScript because, well, it's inspired by it. And you can console.log hello world. So when I ran yarn start, it started building. And when it's built, what we're going to see is just a console log. But what's really interesting is this console log is coming from inside of WebAssembly, which is very, very interesting. We're able to share code between JS and WASM. And that enables some powerful use cases we'll talk about after this builds. So everything worked. It compiled successfully. We have a blank screen. And if I go here, I have hello world. Boom. Now, can we do better? Of course. Of course. So what we're going to do is we're going to go to cargo.toml, and we're going to say we need another dependency. We need window, okay? And we're going to go back to our project and say let window equals WebSys. We're going to use window here, and it has testing built in, so I'll expect something to go wrong and say oops. And then window.alert with message. It's a little bit different, and I'll tell you why in a minute. But we can say Armenia. Don't forget your semicolons in Rust. Save, okay? And that is going to compile, but while that compiles, here's something interesting. Oh, I guess it just worked. There you go. So I'm calling alert window from Rust. The interesting thing is you can call this in JavaScript, and it does nothing. So you can also call that from Rust, but you can't pass parameters to it because it's strongly typed. That's the only thing. And lastly, let's try and put something on the screen. And this, again, is calling into WebAssembly. It's very interesting. For that, I'm going to need some more dependencies. I'm going to need document, HTML element. And this is all documented. If you go to docs.rs, you can find all this stuff. Element and node. I believe this is all the dependencies I need here. And what we're going to do is we're just going to put something on the screen, okay? From WebAssembly compiled from Rust. Very interesting. So we'll just say let document equals window.document. And again, if something goes wrong, oops. Let body, like it's almost the same as JavaScript. Body, no body. And then let's create something to put on the body. So we'll create a heading. Heading equals document.create element h1, okay? And I will say heading, actually that needs a operator. Heading dot set inner HTML to, what should I say? Dolma is my favorite food here. And then lastly, I will body dot append child with my heading. Okay, so there's some code here, but look, this looks kind of similar to JavaScript, doesn't it? But it's not, it's Rust. And so that's going to go ahead and pull down the dependencies that we just added, and then it's going to compile. And what we should see in just a few minutes is a Rust module compiled to WebAssembly, executing kind of on the CPU, but calling out to JavaScript for browser-based stuff. Oh, I broke something. What is the problem? Append child heading. Oh, right, I need to borrow heading. So this is memory management in Rust. I need to, yeah, it's a whole other topic, Rust borrow checking. But when this builds, there we go, perfect. What we're going to see is our alert, our console log, and Dolma. And so the question that we'll close with is what's happening here? Why is this impressive? And to do that, let's take a look at the compiled output. So if we go to package, this is the stuff we're going to be shipping to NPM. Okay? What we see is an index.js. It's your entry point. And we're importing something from this index.bg WASM file. It's not a JavaScript file. What is this? And then we're calling the main.js function. This is the function we export. Look, it's the function we export from Rust. What is it? Well, if we go look at index.bg.wasm, get ready. It says this file is not displayed because it's either binary or uses unsupported text encoding. Should we open it? I think we should. This is what it looks like. Literally just binary instructions talking to JavaScript here, interop. And it's huge, but it's literally, go here, do this for every little thing. And if we search for Dolma, we're going to find, look, it's right here. On line 34,522. Which I think is really, what does this mean for the web? And with this, we'll wrap up. What this means for the web is we can create some things really interesting. We can, for example, export a function from Rust that does very heavy computations very fast, and then do most of our stuff in JavaScript, but say, hey, I need help. Rust, do this for me. Rust does it fast, sends it back. And we have really performant web apps. In fact, that's most of how you'll see WebAssembly used. I'd like to, in closing, share with you some interesting projects. These are, like, they blow my mind. Typed HTML is an implementation of JSX, but strongly typed. JSX, like from React, but in Rust. Dodrio is a virtual DOM library. Yeah, that exists in Rust via WebAssembly. Seed and Percy are web frameworks that allow you to build web front ends in Rust and WebAssembly. And the last two are more dev tools, but I'm really excited about WASM bindgen futures because it's like promise-style APIs for asynchrony, again, in Rust. And with that, I'm going to tell you WebAssembly excites me. It excites me because the web becomes inclusive. Everybody can play. It becomes fast. I can do things. I could play like desktop. I could have desktop class experiences on my phone if I wanted to when the browsers are improved. And it's a game changer. So with that, I want to say thank you so much for listening and coming to this talk. I appreciate it very much.